next speaker is a senior software engineer on the Ruby architecture team at GitHub. He's worked on Rails applications of all sizes and contributed to numerous open source projects. He was formerly a composer, string player, and professor of music. I really appreciate his ability to explain complex topics in understandable ways. Please join me in welcoming Daniel Colson.
Thursday morning. Big crowd feels really good. There's a lot of good energy. But you're all making me really nervous too. So many smart people here. It's terrifying. But that's okay. I've got Cat. I'm going to tell you a story about Cat today. Cat is, you might know the story, the very hungry caterpillar. This is not the same cat. This cat is a software developer working on a large Ruby on Rails application at Bug Hub. And Cat's had a bit of a stressful week. Bug Hub is this large online community of bugs. And Cat has spent the past week shipping a highly successful new product within Bug Hub. But along the way, Cat has had to deal with a bunch of problems. Data consistency bugs, application slowness, and at one point even site-wide failure. All these problems are going to trace back to a single database transaction. It's going to start out as a small, simple transaction. But as the days go by, more and more requirements are going to cause this transaction to grow in size until it's eventually going to become a liability for Cat's application. Along the way, we'll stop and explore what went wrong and how Cat could have improved some of these problems. If I can just slow down my heart, breathe a little bit. The story starts on Monday. Cat showed up to work very hungry for business opportunities. Cat knows that a lot of the bugs on Bug Hub are very hungry for food, but they're too busy connecting on Bug Hub. And they don't want to be bothered to go out to the grocery store. They want groceries delivered directly to their homes. So Cat has decided to launch a brand new grocery delivery service integrated with this larger Bug Hub product. The very first grocery delivery service for bugs. It's great. We're not going to dig into controllers or views or even how this order gets put together. We're only really going to look here today at how the order gets saved. So we can assume that this order instance variable is an instance of an active record model, an order model backed by an orders table in the database. There's also a product model for the various grocery products that a bug can buy. And that's going to be identified by a SKU, or a stock keeping unit. And then finally, there's a join table connecting those products to the order. And this order item model also has a quantity of how many of that particular order is in the, how many of that particular item is in the order. All right, so it's not explicit in the code here, but when we call save on an active record model, that opens up a database transaction. So here's our first transaction. If we look at the queries involved, we see a begin statement starting the transaction. And then we insert the orders and some number of order items for that order. And then we commit the transaction if it was successful or roll back if it wasn't. And this is what a transaction is supposed to look like. The idea here is we want this to be atomic. We want it to be all or nothing. All of the inserts should succeed, or none of them should succeed. We don't want partial success here. So this is a good use of a transaction. And there's not too much risk here. It's just a few queries inside of a transaction. Not too much is going to go wrong. So Cat ships this code. And all is well. The orders start rolling in. It's a good day. On Tuesday, Cat discovers that bugs are ordering more items than what Bug Hub has in stock. This is a kind of frustrating experience because bugs get excited about their orders, but then it ends up getting canceled. Cat decides to resolve this problem by keeping track of the inventory right here on the products table. So he adds this inventory column. And then you can use that data to avoid showing out-of-stock products on the site, or maybe add a model validation so that it's not possible to create orders for out-of-stock products. And then over in the submit code, Cat adds this line to update the product inventory after creating the order. And the way that works is it goes through each item in the order, performs an update by subtracting the number of items ordered from the inventory for the product with that particular SKU. Cat wants these two operations to be atomic. Either they should both succeed or neither should happen. So he wraps this in a now explicit database transaction. So now all the inserts, all the updates are happening together in one transaction. Unfortunately, after shipping this code, Cat starts to see a bunch of errors in the application. And he looks to his bug tracking software and sees, thank you, sees a bunch of locking related errors. Sees deadlock errors, lock timeouts, and also requests taking long, some of them timing out. And the underlying problem here ends up being lock contention. This happens when multiple processes are trying to work with the same data at the same time, and they end up having to compete or contend for access to that data. So we can imagine two bugs making orders around the same time, and they're ordering the same product. Excuse me. So their transactions begin, they insert their orders, and then they get to this part of the code that's updating products. And both of these transactions want to update the same product. Database rows are like bathrooms. No follow-up. It generally only makes sense for one person to use it at a time. Don't give me any counterexamples. So when you enter a bathroom, you lock it. You lock the door, and then anyone else who wants to use it has to wait. And so that's what's going on here. Like, only one of these updates can happen at a time. And whichever one does, it's going to lock the row. And so the other update can't happen. It has to wait. Even after the update succeeds, that lock is still going to be held until bug 1's transaction is complete, which leaves bug 2 waiting around, bug 2's transaction. It's only once bug 1's transaction commits that bug 2 can finally get that lock and perform the update and move on. At best, contention like this makes the performance of transactions worse because they get stuck waiting around. But at worst, it can also lead to errors. Cat was seeing deadlock errors. So that's where two or more transactions are waiting for opposite locks, and they get stuck and can't move forward. So the database terminates one of them. Or lock timeout errors, where a transaction ends up waiting so long for a lock that it gives up, it times out. So these can lead to application errors. Interestingly, the speed of a transaction affects how much opportunity there is for contention. If the transaction is fast, the locks aren't held for too long, and there's not too much opportunity for this contention. The chances of another transaction coming in and needing to work with the same data at the same time are relatively low. And even if one does, it's not going to have to wait too long for the locks. Slow transactions, however, have a lot of opportunity for this contention. There's a lot of time for another transaction to come in and need to work with this same data. And then it might have to wait a long time for the locks. And this is what was happening in Cat's case. Cat had a lot of slow transactions, creating this opportunity for contention. But what was making Cat's transactions slow? Well, there's a lot of things that can make transactions slow. One of the things that was making Cat slow is slow queries. It turns out these update statements were rather slow in Cat's application. And he forgot an index on the SKU column. So cat could have reduced lock contention by adding an index to speed up this query. It's kind of interesting. Even if the queries were fast, it turns out the very hungry bugs on BugHub were submitting orders with massive numbers of products in them. And so too many queries within a transaction can also make for a slow transaction. These transactions tend to hold a lot of locks as well. So there's now a large opportunity for contention. And then worse still, transactions like this, in addition to holding a lot of locks, end up likely to get stuck waiting on a lot of locks as well. And so lock contention has this way of kind of spreading. Like locks held by one transaction slow down another transaction, and then that slowness creates opportunity for yet more contention with other transactions. So it kind of cascades a bit. Operating on large batches of records like this inside of a transaction is not really something a transaction is good at. You might be able to get away with hundreds of updates in this transaction, but if you start getting into the thousands, it might be time to reconsider the design. In this case, maybe cat needs to add a max number of items it's possible to have in a single order. So it turns out this innocent-looking line can actually cause some problems if it creates slowness in the transaction. Cat can reduce the possibility for contention by speeding things up, speeding up queries, limiting how many of them there are. And separately, cat can also fix some of the specific errors, like deadlock errors can be fixed by updating the products in a consistent order. But cat might also want to question his assumptions about whether this needs to be within a transaction at all. Maybe there's another design that doesn't require these updates to happen here in this transaction, or that doesn't involve updating the products table at all. Like maybe cat actually needs a more robust inventory management system that lives outside of this database. Wednesday. On Wednesday, cat noticed customers complaining that submitting an order sometimes took way too long. And cat tracked the slowness back to this one after create call, which is doing a bunch of slow work, syncing with an external billing platform, sending off confirmation emails, and a bunch of other stuff. This is stuff we often don't want inside of a request because it slows down the request. And we also don't want it in a transaction because, as we've seen, slowing down the transaction can create more opportunity for lock contention. So cat moves all the slow stuff off into a background job. And this is an improvement, but there's still some potential problems here. After shipping this change, after a while, cat got reports of order confirmation emails getting delayed by several minutes. Since cat is using an after create callback, the job here gets queued right after creating the order, right after the inserts, but before the transaction commits. Now, cat is not using a database-backed job queue adapter, so enqueuing here is not part of this transaction. It's a separate thing. And that means that actually the worker can pick up this job and execute it before the transaction commits. It's not too big a deal in cat's case because the job will fail. It requires a persisted order to run. So it will fail and it can get retried later. But it's not ideal. Then this transaction moves on to updating the product inventory, which we've seen is sometimes really slow. And so actually, it turns out this job can retry and fail multiple times before the transaction commits. And so cat has tried to accommodate this by configuring the retries for the job quite high, so that eventually, once the transaction commits, it will retry one more time and succeed. But a whole bunch of these transactions are rolling back because of all these deadlock errors and lock timeouts and things. And this is a bit problematic. These jobs get enqueued, but they will never succeed because the order doesn't get created. So they get stuck retrying and failing until eventually the retries run out. So these are destined to fail, but they're kind of stuck in the queue doesn't know that the rollback happened. They just keep retrying. So what happened in Cat's case is these retries ended up backing up the queue and getting in the way of successful job runs, delaying the work of those successful job runs, like sending confirmation emails. So Cat probably needs more job capacity here, but we'd rather our capacity be determined by successful runs and not a slew of failures. So the simplest thing Cat could have done differently here is swap this after create call with an after create commit. Now, enqueuing the job doesn't happen until after the transaction commits. If the transaction rolls back, it won't get enqueued at all. And so typically it will be run exactly once without the need for all these extra retries and fails. You can look forward to Rails 7.2, which is going to offer a way to do this by default, to enqueue jobs after transactions commit by default. In that case, Cat wouldn't have had to make any changes at all. So that's great. Coming soon. On Thursday, customers started complaining about orders getting delivered too late or sometimes with the wrong items in them. And it turns out Cat's team has been doing a whole bunch of manual work to fulfill these orders, but it's been really slow and error prone. So Cat has decided to work with this external fulfillment service, and they have an API he can use to submit the orders. So after saving the order to BugHub's database, he adds this call to submit the order to this fulfillment service via a fulfillment client. This is an HTTP call to an external service inside of a database transaction. If we look at the queries involved and where this external call gets made, you might notice it's kind of similar to the job example. And that's because the enqueuing a job with Cat's particular job queue adapter was an external call. It's the same sort of thing. And so this one has some of the same problems. Like the external call here could succeed, but then this transaction might still roll back. But worse than that, after shipping this code, Cat starts to see errors across all of BugHub, not just in this grocery delivery product, across the whole site. Cat started looking into this and noticed that this external fulfillment service was having some scaling problems. It was not able to keep up with the number of orders coming in through BugHub. It makes sense that this would affect creating orders, but how is this cascading into failures across the whole site? So as the external service got backed up with too many requests, it started responding really slowly or sometimes not responding at all. Intermittent slowness is somewhat expected for external calls. Like services can respond slowly, they might have problems, but there's also a network to deal with, and network latency is an issue too. And it's one of the reasons we often move external calls outside of requests and into background jobs. But regardless of whether it's in a request or a background job, we still need to be careful about putting these calls inside of transactions. When slowness like this happens inside of a transaction, it can threaten the health of your database. From the database's perspective, this transaction is sitting idle for the duration of the slow external call. So you might not think it's not doing much, but it's actually still using valuable resources. For one, it could be holding locks. Actually, that's not really the case here since the idle time is before all of the updates, but in other transactions, that could be a problem. But the bigger problem in this case is that the entire time this transaction is open, it's using up a database connection. And that database connection cannot be used for anything else. So what happened in Cat's case is as the fulfillment service degraded, orders kept coming in through the site. They would open up a database transaction and then get stuck, sitting idle, waiting for the fulfillment service to respond. And they'd get stuck there for a long time. And then as more and more orders came in, the number of connections in use increased, the number of available connections decreased, until eventually every single database connection was in use. At that point, no other request was able to acquire a database connection. And so any request across BugHub that needed access to this database started to fail. Even the connection pooling mechanism in front of the database here didn't help anything, because each of these transactions is taking up a real database connection the entire time it's open. Probably Cat should have configured a client timeout on this HTTP call. We should never wait for an unlimited amount of time for an external service to respond. And that would have mitigated this to some extent, but there's still some risk having this call here inside the transaction at all. And the real solution is that Cat should move this external call outside of the transaction. Now if the fulfillment service has problems, it has no effect whatsoever on the database. This transaction only begins if the call succeeds. So failure of the service would still affect creating orders, but it's not going to affect the rest of the site. So we've removed this possibility for cascading failure. I also like that it's visually more obvious now that these two operations are separate. They're not one atomic operation, two things that can each succeed or fail. In both versions, it was possible for the fulfillment service call to succeed, but then for the transaction to roll back. But I think I can see it better now, and I'm more likely to handle that in my code. On Friday, customers start complaining a lot about site reliability. In addition to all the problems that we've seen here, the application has been slow, and users are seeing intermittent 500 responses regularly, and they're starting to get frustrated. The problems stem from this grocery delivery service's popularity. There's a lot of orders coming in. There's a lot of products getting added. But it turns out that the database is getting overwhelmed by all these writes on the product orders and products tables. So thinking quickly, Cat and the database team get together and decide to extract the orders and products into separate databases. That leaves a bit of a problem here with this code. We've got an orders transaction, but we're doing both orders and products queries inside of it. So Cat decides to wrap it in another transaction. Now there's an orders transaction and a products transaction. And yeah, some people have maybe done this, and thus the giggle, or maybe know what the problems are. But it kind of looks reasonable on paper. Like, it looks like this should work. It looks innocent enough. But it's a really bad availability risk. It threatens the health of these databases. Bug can pretty much guarantee he's going to see all of the same bugs before, but they're going to be worse now because they all affect two databases instead of one. So if there's slow queries, if there's external services degrading, we're affecting both transactions, both databases. Plus, queries to one database inside of a transaction to another database are just another kind of external call as far as that other database is concerned. And it comes with the same problems. If one is having problems, it can now affect the health of the other one. So the health of these databases is tied together. And we've kind of limited the effectiveness of extracting them in the first place. Furthermore, after Cat ships this change, he notices that certain products stop selling because the inventory went down to 0, even though the product's actually still in stock. And that has to do with the fact that these two transactions are not atomic. It's two separate operations to two different things. So a lot of the time, they'll both commit. Or if the inner products transaction rolls back, that'll probably cause the orders transaction to roll back as well. But in Cat's case, what was happening is that the inner products transaction was committing, decrementing the product inventory. But that order actually never got created. That transaction rolled back. And this was actually a fairly common scenario in Cat's application. For the duration of the products transaction, that orders transaction is sitting idle, which we know is not great for other reasons. But actually, after a long period of idle time is one of the more likely places for a connection to fail for some reason. Maybe timeouts at the database layer or timeouts in the network layer. So all sorts of things could go wrong here. There's no guarantees that both of these transactions are going to commit. So given that this is already not atomic, the first thing I'd recommend that cat do is make that explicit by doing them sequentially instead. This is not always an easy change to make. The stuff inside of the nested transactions tends to be intertwined, so untangling can be difficult. But it's an important change to make for the health of these two databases. Again, I also like that putting these things sequentially kind of highlights the fact that they're two separate operations, not atomic. So we're more likely to consider now this case where the products transaction succeeds, decrementing the inventory, but then the order actually rolls back. And cat doesn't want that. Cat doesn't want the product inventory to get decremented without the order getting created. So one thing cat could do is swap the order of these transactions. That's easy to do now. Of course, now it's possible to create the order and then not decrement the inventory. So we've traded one possible failure for another. But maybe that's fine for cat's application. Maybe it's OK for the inventory to be too high rather than too low. Or maybe cat needs to write more code to deal with that possible failure and to make these things behave more like they are atomic, even though they're not. On the weekend, cat doesn't work on the weekend. I don't work on the weekend. Cat likes to rest and reflect on what he's learned. So cat learned that external calls within a transaction are a risk. They can lead to data integrity problems because the things sort of look like they're atomic, but they're not. It's like it can sort of hide the fact that you're dealing with two separate operations. They can lead to cascading failures, where the failure of the external service ends up causing problems in your database itself. And this includes a whole bunch of things. HTTP requests, that's the main one I mentioned, but also sending emails and queuing jobs, querying other databases, all kinds of things. Really, the only thing we want inside of a database transaction is queries to that database. Cat also learned that slow transactions are a risk. If they're in a request, they can create slow requests, which we don't like. But really, we don't want slow transactions anywhere. This problem with contention in one place can affect a whole bunch of other places. So like slow transactions, even if it's in a job, can still create this opportunity for contention in other parts of your application. So it can affect the performance of requests. And then there's this problem of resource exhaustion. Database connections are a finite resource. Database CPU is a finite resource. Slow transactions can overuse these resources and threaten the health of your database. That brings us back to Monday. A full week. Cat had a nice restful weekend, but some of Cat's colleagues, oh yeah, there's Cat. He's well fed. But over the weekend, a bunch of other teams were committing code to this transaction, working over the weekend. And on Monday, he came back to something like this. So who's seen a transaction like that looks something like this? Yeah? Ooh, a lot, yeah. Many of us know that transactions like this are bad for maintainability. Nobody knows how they work, and nobody wants to touch them. But transactions like this tend to carry a lot of risk. I think we underestimate how much risk. And they can affect other parts of your application. And maybe even have the risk of bringing down your application. So it's pretty serious. So what is Cat to do with a transaction like this? Cat's probably tempted to crawl into a cocoon and just pretend it doesn't exist. Or maybe wait for somebody to rewrite the whole thing. I'd recommend against trying to rewrite something like this from scratch. There's probably a lot of knowledge in that transaction. You don't want to just rewrite it. Instead, see if you can make small incremental changes to make it a little bit better. Maybe move one external call outside of that transaction. Maybe speed up one query. The idea is to make the minimal change to leave it a little better. There's some tools coming in Rails 7.2, maybe Rails 8. I don't know what the version is going to be. I think it's 7.2 at the moment. Not sure. I already mentioned this option to delay in queuing active jobs until after they commit. But there's also a more general purpose callback in the works to defer work until after transactions commit. So I think this is going to be helpful for improving transactions a little bit at a time without completely rewriting your code. In addition to fixing the existing transaction that Cat knows about, I'd recommend that Cat also try to identify other problematic transactions like this, since a transaction in one place can affect things in another place. Most databases have tools for inspecting the behavior of queries and transactions. Like in MySQL, there's the performance schema databases that you can query and get information. You want to look at what transactions are slow, which ones are holding or waiting for locks, which ones are sitting idle, and prioritize based on that. We also added transaction instrumentation to Rails 7.1. So it can be useful to see them from the application side as well, and then maybe combine that information. And then finally, I'd recommend that Cat try to prevent transactions like this from creeping back into the application. There are some tools for this, like the isolator gem that tries to detect external calls inside of a transaction. But I'll also leave you with a few tips about how to write safe database transactions in the first place. First, we want to keep transactions short. I wrote under a second here, but that's just made up. Maybe it depends on your application, but short as possible is probably best. And nowadays, when I see transactions over 5 or 10 seconds, I start to get a little nervous. Having fast transactions means having fast queries in those transactions and not too many of them. Again, I made this number up. I don't know. It probably depends on your application. When I start seeing more than 1,000 queries in a transaction, again, I start to get a little nervous. We don't want to have any external calls at all inside of our transactions. And really, we want to do as little as possible inside of our transactions. Like ideally, we try to move as much as possible before or after the transaction. Callbacks can sometimes make it hard to see what exactly is going on inside of the transaction. So when you're writing callbacks, you might want to default to using callbacks like after commit that do the work outside of the transaction. And then finally, it's worth asking if you really need a database transaction at all. Sometimes it's easiest to dump everything into a transaction because it's easier to reason about, things being all atomic. But that's not always the best design for our application or for the health of our database. We want to treat our databases as this kind of sensitive resource. Don't make them work harder than they need to. There it is. Okay. Hopefully, these tips will help you write safe transactions in your applications. And you can avoid some of what Cat had to go through and, I don't know, low stress. I'm Daniel Colson. I work at GitHub, not BugHub. But like everything here is based on real problems that we've seen at GitHub with names and domains and species changed. But yeah, I'd love to talk more about any of this. I'll probably do questions like up here after, because I'm terrified of questions. So I'd also like to thank my father-in-law and his friend for doing the illustrations. Thanks.